Okay, so this is an IVP for Laplace transforms. We have our equation and we have our initial conditions. Our goal is to solve this IVP. So our first step is that we want to take the Laplace of both sides, and that looks like this. So Laplace of y double prime minus 4 Laplace of y prime plus 4 Laplace of y equals the Laplace of 12. So we have a table in our formula sheet that lets us do this very easily. So the Laplace of y double prime is s squared y of s minus s y of 0 minus y prime of 0. So then the next one, the Laplace of y prime, so we're going to have our minus 4. Then here in parentheses, we're going to have our s y of s minus y of 0. And then the Laplace of y is just going to be y of s. So we'll have plus 4 y of s equals 12 over s. The Laplace of a constant is just 1 over s, so it becomes 12 over s. Now we plug in our initial conditions here and here. So this becomes s squared y of s minus 4s, correct? Yep. And then this is just 0. This minus 4s y of s minus 4. Plus 16, because it's you plug in the 4 here and then you're multiplying it, and then plus 4 y of s equals 12 over s. So next step here is to isolate the y of s. So we have, our objective here is to solve algebraically for y of s. So we're going to group all of the y of s terms together on the left side and move everything else to the right side. So that's going to look like this. So if we start with our y of s, we're going to take this. So we have an s squared, a minus 4s, and a 4. So in this parentheses, we have s squared minus 4s plus 4. And then we're just going to move this 4s and this 16 over the side. 12s plus 4s minus 16. So notice this quadratic can be factored very nicely into parentheses s minus 2 squared. So let's just go ahead and do that. And then we're going to just bring down everything else. 12 over s plus 4s minus 16. So again, just going to divide this over. Equals, so 12 over s minus 2 squared, right? This is going to be plus s minus 16 all over s minus 2 squared. I did this so that it can be a little bit cleaner, so that we don't have a 12 over s over this, just adding this to this denominator. So to make the next step easier, which is going to be our partial fraction decomposition, we want to combine the right side into a single fraction by finding a common denominator, right? So that common denominator is going to just be s times this. This is well, let me add this. This is going to be our common denominator because, as you can see, these are the same thing. All this is missing is an s. So go down, and we are just going to have so we're going to multiply s over s. So this becomes 12 plus 4s squared minus 16s all over s minus 2, all that squared. Make this look a little nicer. Over s minus 2 squared. Okay, so now we're ready for our partial fraction decomposition. Now, we can't easily take the inverse Laplace transform of this large fraction, so we need to break it apart using the partial fractions. Because we have a single root s and a repeated root s minus 2 squared, we can set it up something like this. So this is going to be a over s plus b over s minus 2, and then plus c over s minus 2 squared. So we're going to multiply the entire equation by the denominator to clear the fractions. And what we're left with is, and as you can see, what we're left with, what's going to go into the numerator. So this has an s, this has an s minus 2, this has what's going to be left in the numerator is going to be whatever this denominator doesn't have. So let me show you. Y over s equals, so again, we're just going to bring this part forward. And that's going to be set equal to a, and what was it missing? The s minus 2 squared plus b. This is missing an s and another s minus 2 term. And then this is missing just the s. Okay. So now we pick strategic values for s to easily solve for the constants a, b, and c. So if we set s is equal to 0, what happens? Well, we're left with so this whole thing, so if we set s is equal to 0, this cancels this drops to 0. We're also going to have this term and this term drops to 0. So all we're left with is 12 equals 2 squared, which is the same as 12 equals 4a, a equals 3. So now if we set s is equal to 2, again, we're taking a guess so that we can simplify this down. This becomes, oh, not that. So 4, 2 squared. And again, this is the messiest part of this whole thing. It's a lot of steps, but what can you do? Because also wanted to point out, as s equals to 2, and this is the reason why we chose 2, is because this term drops and this term drops. Because 2 minus 2 is 0, this just multiplicity by 0. So now we have this, which we can break this down to 16 minus 32 plus 12 equals 2c. And that just becomes equals then just c equals -2. So our next step is to find b. Let's get the pointer out. So to find b, we can look at the coefficients of the s squared term on both sides of the equation. On the left side, the coefficient of s squared is 4. On the right side, the s squared term comes from the a s squared and then the b s squared. So the coefficient is a plus b. So again, we already found BA, so then this is just 4 equals 3 plus B, so B equals 1. Now, again, I wanted to just reiterate that we have, in this equation, we have our 4s squared, and then over here, the coefficient that's outside here is just the B and just the A. So we can literally exactly what we're doing, setting 4 equal to the coefficient. Like, I don't know how best to, I don't know if this is the best way to explain this, but because you have the s squared term on the left side and the s squared term on the right side, whatever the coefficients are, you can set them equal to each other. That's what we're doing here to solve for our b. So now we have a, b, and c. So I'm going to go to a new page. Our new, and we can write our y of s equal to 3 over s plus 1 over s minus 2 over s minus 2 squared. Now we need to take the inverse Laplace. So finally, we apply the inverse Laplace transform to each term to get back to the time domain y of t. So let's do that. So again, we're taking the inverse Laplace of y of s, and so all this, I'm not going to rewrite it again, but basically we have formulas to undo these things because, as we know, when we take the Laplace of a constant, the Laplace of a constant is just going to be that constant over s. So taking the inverse Laplace is, again, just undoing it. So we have a formula table, and so let's utilize it. So the inverse Laplace of 3 over s is just going to be 3. And again, this is what we're setting up our y of t. So it's going to be 3. The inverse Laplace of 1 over s minus 2 is just going to be e to the 2 t. The inverse Laplace of 2 over s minus 2 squared, well, we can combine our rule for t to the n and the shifting theorem. We know that, okay. This is a formula that was given to us in one of the lecture videos, but nonetheless, this is not on the standard formula sheet, so I don't believe you'll face a problem like this on the exam. But basically, this is the formula that we're using. The inverse if I can write the inverse Laplace of 1 over s minus a squared is equal to t e to the at. This is exactly what we're doing. So this means that this is going to be minus, and we're going to, again, bring down this constant. And so we have the t, and then our a here is just going to be 2. So it's going to be e to the 2t. So putting it all together, the final solution to our initial value problem is y of t equals 3 plus e to the 2t minus 2t e to the 2t. So I just want to run us back what we did with the pointer. So we have this IVP, we have our initial conditions. First step for the IVPs is just taking the Laplace of, oh, that's the wrong thing. Okay. We're taking the Laplace of everything. And this, and this, we all have formulas for this. So, and with the experience and practice, you should probably have some of these memorized for speed on the exam. But basically, you're plugging in each, and obviously it's just more convenient to take out the this constant, and then after you plug in what the Laplace of all of these are, you plug in your initial conditions, which we had, or y of 0 equals 4, y prime of 0 equals 0. Once you get this down, you just want to clean it up a little bit. And then our next goal after here is to isolate the y of s term. So what we did was we found all of the terms with y of s, and we just collected all of those terms inside this parentheses, and then subtracted everything over to the right side. So then we realized that this can be factored, which is going to make our life easier later on. So we factored this out. This still over here. So again, what we did here was dividing everything over. Now we wanted to find a common denominator so that our partial fraction decomposition would be far simpler, or not simpler, but easier to look at and see. So we multiplied both sides of, or the top and bottom of our right term here by s over s, which led us to this, cleaning it up for the next step. So now we have y over s, and we broke this down to a over s plus b over s minus 2 plus c over s minus 2 squared. And then our next step from here is to multiply our common denominator by all of this. So we're multiplying it here, and basically what you're going to be left with is whatever in the numerator from this common denominator. So like, for example, for here we had the a s minus 2 squared, and again, just for context, we're setting this numerator equal to this situation. So we have our numerator, it's going to be equal to, and again, this math gets broken down over here. So now we took two easy guesses, s equals 0 and s equals 2, so that we can just eliminate some stuff to find some of these coefficients. So we set s equal to 0 to find our a. We set s equal to 2 to find our c, and then we set we noticed that because the s squared term was on both sides, we can just pull the coefficients and solve it down. And then we basically just took the fact that we have our our a, b, and c, plug it back into our equation, and then we needed to take the inverse Laplace. Taking the inverse Laplace of everything, these were easier to do because from our formula sheet. This one was provided, again, this formula would be provided to you, maybe not like this exactly, but it could be the other way around, where it's just the Laplace of t e to the at equals 1 over parentheses s minus a squared. But either way, this is something that would be given to you on an exam. And from there, it's quite literally just plug and chug. Minus 2t e to the 2t is going to be your final solution to this IVP. I hope that helped. I will leave a PDF or an image file of these notes for you. Thank you guys so much.